All right, now the next thing we look at here is the next chapter. It's flow and velocity. Okay, so let's have a look at that. So what we've been looking at so far is something called fluid statics. Statics means it's not moving. Now we'll have a look at when fluid does move. So this is on page 86 is where it's at. So the first thing we'll just look at is velocity and things like that. We have this basic way of analyzing this. And what that is Q, that's the flow rate, is equal to the velocity times the area. And generally speaking, when you're doing this type of calculation here, you like the velocity in feet per second. That's the normal unit to have that in. And then the area in square feet. And then Q comes out to be cubic feet, which is an area, a volume unit divided by seconds. Okay. So the idea here is if you take the area of a channel or a pipe and multiply it by the speed of the fluid in there, what you'll come up with is a volume flow rate. So it might look something like that. If you've got a channel that's a foot by a foot, and you've got a velocity of a foot per second, what that means is every second, what you're going to have coming out of that channel is a block of water. Let's just say it's more like Jello or something, so it sticks together. That would be a foot by a foot by a foot. Okay. So that means that if you have an area of 1 square foot and a velocity of 1 foot per second, what you get every second coming out of that channel would be 1 cubic foot. Okay. So we're taking the area times the velocity to get the volume flow rate is what we're doing there. Okay. Any questions on that? All right. All right, so if you've got how much water is coming through a 6-inch line at an average velocity of 5 feet per second, let's figure out, so if we have a 6-inch line, why don't you find the area of a 6-inch line? Get it in square feet. So what's the area of a 6-inch line? So that area ought to be about 0.196 square feet. And then just factor that up by the velocity and you'll get the flow rate. At about 0.982, thereabouts. Okay. So you just find the area and then multiply by the velocity. Just be sure that your units match. That's the thing. Okay. The general unit for that is feet, square feet, and feet per second. How about this? We got CFS. Now that's a common abbreviation there for cubic feet per second. And what's the velocity on that going to be? Now what you got there is Q equals VA. That's the basic formula. You might have to rearrange that to solve for what you want if you're after velocity. So you want to solve that for the velocity is what you want to do. So just algebraically rearrange it, you know, pretty straight up, but just solve for V, the velocity. Q over A. Remember, Q is the flow rate. CFS is cubic feet per second. It's an abbreviation that's commonly used. So you get the area easy enough, just divide it into the flow rate. You should get 1.25 feet per second, I think. So, you know, when you take the cubic feet per second, you divide it by square feet. Square feet cancels out 2 of the 3 of the cubic feet, so that leaves you with a foot per second. Everybody all right with that? Okay, good. Right, so that's just, you know, that formula there. It's just Q equals VA. Now, there's a couple other things we got to look at with this. First one is called continuity of flow, which is kind of a fancy name for a pretty simple idea. If you got a pipe and the pipe is full, if you put in 3 cubic feet per second in one end, 3 cubic feet per second is going to come out the other end. I mean, if the pipe's full, there's just nowhere else for the water to go. And, you know, they use that for those of you that are in the water program. You know, they use this a lot in water treatment. You know, if you've got a tank here, and say we got a trough in the, you know, on the edge like you have sometimes. If you're pumping in whatever, you know, 1 MGD, million gallons per day, that's what's going to come out and go into the trough, right? I mean, just because the tank's full, let's put water in, it's got to come out. I mean, it's that simple, all right? So the same thing for a pipeline. You put in a certain flow rate at one end, it's going to come out the other end, okay? All right, now you can start messing with the velocity and changing it if you change the areas of the pipe, because what you're going to know here for a pipe is that the flow coming in, if the pipe's full, which they generally are, is going to be the flow going out. Okay. So if you know that the flow in is the flow out, you can start to look at velocities and areas and what those relationships would be for those. Let's say we got 4 inches here and 1 inch here. Okay, and let's say we're going to put in 2 feet per second into the left side of the pipe. Let's figure out the velocity coming out of the pipe. Okay, and this is on page 89. Now I might have a typo in there. Let's use inches instead of feet. I think a 4-foot pipe would be a pretty big one, so why don't we knock that down to 4 inches if it hasn't been done already. I don't think it has, so you might need to change this on page 89. Okay. So once you find those 2 areas there.
Where does that make the smaller one?
1 inch. So both the feet
gotcha,
go to
right,
inches.
yeah,
You're still kind of bringing it down. So remember to convert those into feet first. They're 4 inches and 1 inch currently. We want to change them into feet. because the flow rate's in feet per second, as it often is, so you just want to get everything converted into feet so the units match. All right, 0.0873 and 0.00545, something like that. Okay. All right, so we start with that, and then once we've got that, you'd want to find the flow rate coming in. Okay, so that'd be the next thing to do. Find the flow rate coming into that pipe. So to find the flow rate, just take the velocity times the area. So I get 0.175 cubic feet per second. So that's what's coming through that pipe. And then once you've got that, you want to find the velocity coming out. So see, that's the flow rate coming in. Of course, it's the same flow rate going out. So what you want to do then is you want to divide that by this area on the other side. Okay. And you ought to come up with something on the order of 8, is it? No, 32. So when you divide that out, you get something on the order of 32. Yeah, it's kind of the idea with a fire hose, you know, you got a big hose coming in and a narrow nozzle. Yeah. By the time you neck it way down to, I don't know what it is, an inch or whatever, yeah, you could get a lot of velocity and, you know, a lot of force out of those things if you need it.
I know, on the end of a 1.25-inch wire hose, was something like 120 PSI.
Oh, okay. Yeah, okay.
It was like holding on to a 50-pound block.
Was it? Yeah, okay, yeah. Not bad. Yeah, I've seen those. Have you guys seen high pressure washers? Those, you know, those for cleaning sewers. Yeah.
Take paint off here.
That's what we were doing with the fire hoses.
Oh, yeah, okay, yeah. Those things, those high pressure washers, they get up around 2,000 PSI, I think. So, yeah, it's pretty serious.
All the power towers.
Yeah, right.
Yeah, probably would. Yeah, those little jets.
Yeah, it's like a plasma cutter or like one of those water jet cutter things.
So we're doing all right with that? Doing okay? Okay. Now, a couple other things on this. Of course, there's a shortcut method on this one too, because what you're doing, you're taking 2 feet per second. And then to get that into a flow rate, you multiply it by the area, and that's pi times r in squared. And then you divide it by the area out, which is r out squared. So it's kind of like that hydraulic jack thing we were looking at. The pi's would cancel if you got a round pipe. You know, you're working with pi r squared. So what you could do is take the velocity in times the ratio of the radii in and out, and square the ratio, you'll get the velocity out. So if you take 2 feet per second times 4 to 1, right? Yeah. And that's the diameter. You could use the radii or the diameter as long as you're using the same thing for both sides, you're good. Then you square that. The units cancel, so we don't need to worry so much about inches, but if you want them in there, they're inch and inch. So what you're going to get there is 2 feet per second times 4 squared, and it's just 16. So 2 feet per second times 16 will get you 32. A little quicker there, if you like. You have to remember that, though. They don't usually put that on formula sheets.
Does this go for pressure too, for like hydraulic cylinders?
Okay, the pressure has a different change. The pressure will change. This is called a venturi if you neck it down far enough. It's used for jets on carburetors, you know, and to vaporize the gas. They're also used for chemical injectors. You have a venturi. And what you actually do in these things is you drop the pressure when you force water or anything through a narrow opening.
Right.
Pressure drops.
High flow, low pressure.
Yeah. Yeah, right. You can use it to two common things. One is to draw commonly it's chlorine, you know, into a pipe. Another thing you can do is you can vaporize gasoline by the use of this, because you drop the pressure so low, it'll just poof, it'll just vaporize, and then it's ready to explode when it goes into the cylinder of the car. All right. All right, so that's a little bit on that. So, on Friday we'll cover that homework, and it's due Monday. Okay. So there it is. So it's chapter 8 homework 8.1 through 8.9. I've got the problems and the answers in Moodle. Okay. All right, so I'll call it good here. It's like we have a little sun out there, so that's nice while it lasts.